Hi, I am Artur Saturnino. I am a graduate student at the University of Pennsylvania, and this is the first part of a two-part series on CMC surfaces of bounded index. In this first part, I'm going to talk about CMC surfaces from a variational perspective. I'm going to introduce the index and state some classical results that relate the index to the topology and geometry of the surface. And I'm going to finish off by stating my results that I'm going to talk more about on part 2. Before starting, I want to thank the organizer, Hojo Lee, for giving me the opportunity to talk about my results. So without further ado, let's start. So I'm going to start by defining a CMC hypersurface. Now let M be a Riemannian manifold of dimension n+1 and consider an immersed surface sigma immersed by this function little f. Now let f be a compact variation of sigma, that is a one parameter family of immersions varying between minus epsilon and epsilon, where f at time, so you can think about this parameter between minus epsilon and epsilon as time, and big F at time 0 is just little f, and we assume that this family of immersions is constant outside an interior compact set. So once you have such a family, one natural thing that we can do is take the first derivative of area with respect to this time parameter, and you can compute it explicitly to find this formula there on the right. That is that the first variation of area is given by minus the integral over sigma of the product between x and h, where h is the mean curvature of the surface sigma, and x is the so-called variational vector field, which is the time derivative at 0 of the variation. This motivates the definition of minimal hypersurface. That is, a minimal hypersurface is a critical point for the area functional for any such variations. So we always need this derivative to be 0, which means by the formula that the mean curvature h has got to be 0. To motivate CMC hypersurfaces, let's assume that sigma is the boundary of an n+1 manifold omega, and that our variation extends to a variation of an immersion of omega in M. When we take the derivative of volume with respect to time at 0, we again can get a formula for it, which is just the integral over sigma of the outward normal of sigma times the variational vector fields. So for this reason, we say that a variation f is volume preserving if this integral is 0. Now this integral makes sense even in the case where sigma is not a boundary and is only a two-sided immersed surface. So we talk about volume preserving variations even for the case where sigma is not a boundary. This leads us to the definition of constant curvature hypersurface. That is, these are critical points of the area functional for volume preserving variations. This, now from the two formulas that we have, it's clear that this means that the mean curvature h has got to be a constant multiple of the normal. Now let's talk about the index of a CMC hypersurface. As you're going to see, this is a quantity that comes from the second variation. So for a setup, now let's assume that sigma is a two-sided compact hypersurface. There is a definition of index for one-sided minimal surfaces, and we can also define index for non-compact CMC hypersurfaces by taking an exhaustion, but that's for the purpose of this talk, we won't get into that. And let's assume that F is volume preserving and that X is normal to sigma. The variational vector field is normal. Now it turns out that in this case, the second derivative of area at time 0 really depends only on the variational vector fields, which is using these remarkable facts, we can make sense of this bilinear operator Q. So Q is called the stability operator. In this set V of compactly supported functions with mean 0, by defining Q VV to be the second derivative of area for a suitable variation. And here by a suitable variation, I mean a variation that has variational vector fields V times N. Now it turns out that there is a nice formula for this stability operator, which is given on the right of the equation by these. And notice that this formula really makes sense for every V. So there's nothing in this formula that doesn't make sense in case V doesn't have mean 0. So this means that we can extend Q naturally to the set of compactly supported smooth functions. Now we can talk about the Morse index. And the weak Morse index of sigma is the maximum dimension of any subspace of V where Q is negative definite. So we're basically counting how many independent directions we can squeeze sigma to decrease area while keeping volume. So if you think about the most simple CMC surface, which is a sphere, a round sphere embedded in Rn, these have weak Morse index 0 because the only way to decrease the area of a sphere is also by decreasing the volume it contains. Since we can extend Q naturally to the set of compactly supported smooth functions, we can also make sense of the Morse index in this larger vector space. And again, by counting the maximal dimension of any subspace where the operator is negative definite. And this new index is called the strong Morse index of sigma. So if you go back to the example of the sphere actually has strong Morse index 1 because we can contract the whole sphere, which is gonna decrease area, but also gonna decrease volume. Now just from the min-max principle, one can show that the weak index is less or equal than the strong index, but the strong index can't be that much larger than the weak index. It's at most the weak index plus 1. And it turns out that in many non-compact cases, the strong index is equal to the weak index by result from Barbosa and Behat. And finally, we say that a CMC surface sigma is weakly stable if its weak index is 0, and respectively we say it's strongly stable if its strong index is 0. Let's go for some examples. The first example I want to bring comes from nature, and that is the interface between gas and liquid state. So for example, the surface of a drop of water. When the drop of water is small enough that we can disconsider gravity. And that's because this surface area is directly proportional to a type of energy, and nature is going to always minimize energy, meaning it's going to minimize surface area, but it has this restriction that the drop of water has a set volume, hence it's going to be a weakly stable CMC surface. In this case, just part of a sphere. The next couple of examples are non-compact, and the first one is the equilateral trinoids, which is embedded in hyperbolic in Euclidean tree space, and the second one is the hyperbolic Delaney surface, which is embedded in hyperbolic tree space. So these both have infinite index because they have these infinitely many necks where you can squeeze to decrease area. And this kind of look that they have of bubbles glued together along a string, this is how we expect CMC surfaces of high mean curvature to look like. And this last example is the Venta torus, which is a CMC torus immersed in R3. It's one of the first non-trivial examples of CMC surface that was found. And it turns out to have weak index at least 8. Now, I want to go to some constructions of CMC hypersurfaces. The simplest example is the boundary of a isoparametric region. That is, a region that minimizes surface area for the volume it contains. It turns out that we can always do this minimization and get a smooth boundary on dimensions between 3 and 7. The next example of a variational construction is the Pitt-Salmgreen min-max theory. This is a theory that allows for construction of minimal hypersurfaces and has been very successful in finding many examples. And recently, Zhou and Zhu developed a min-max theory to produce CMC hypersurfaces, and using this theory, they are able to produce CMC hypersurfaces on any manifolds that are always going to be smooth in dimensions between 3 and 7, and they can produce CMC hypersurfaces with any mean curvature. And since the index is a variational quantity, we expect the index of these surfaces produced through variational constructions to be bounded by construction in a way. So, for example, boundaries of isoparametric regions are weakly stable, because they come from this minimization procedure which keeps volume. And Marcus and Neves and Zhou show that in the dimensions between 3 and 7, minimal hypersurfaces that are associated to this quantity called the volume spectrum, which is something that appears in the Pitt-Salmgreen min-max theory, which was later developed by Marcus and Neves. Turns out that these surfaces which are associated to the spectrum have natural index bounds as well. And it also seems possible that the surfaces produced by Zhou and Zhu have index bounds, but that is still it's still a new theory, so there isn't much known. But on the other hand, it's very hard to control the geometry and the topology of the surfaces which come from these variational constructions. So a very natural question is how the index relate to geometric and topological quantities. So in one side we have this variational quantity called the index, but we're talking about hypersurfaces, so geometry and topology are really something we're interested in. And a fundamental result in this area was proved independently by Fischer-Kober and Chain and Tokarmo and Peng. We're going to use this result. It states that complete stable minimal surface in R3 are planes. This is the only complete stable minimal surface in R3, and turns out to be the only complete strongly stable CMC surface in our tree as well, the same arguments. Fisher-Colbury later proved as well that any minimal surface in our tree with finite index also has finite total curvature. So in particular, they've got to have finite topology. There is another line of argument started by Ross and later developed by Savo and others, which for minimal surfaces, but which turns out to also work for CMC surfaces and CMC hypersurfaces by work of Cavalcante and de Oliveira and Dyax and Hong, that uses harmonic forms to construct test functions. And using this, it's possible to get bounds on the first Betti number, which usually looks something like this. So they are kind of affine bound, which depend on the manifold. Hong is going to talk about his result here in this conference, so I recommend you go take a look at his talk. And there is another very different approach by Song, which uses a combinatorial argument to show bounds for the sum of Betti numbers. But these bounds now not only depend on the ambient manifold, they also depend on the area of the hypersurface. Here, for Song's argument, you also need some dimension bounds, the usual dimension bounds. One of the main differences between Song's argument and the arguments by Ross and others is that to use these harmonic forms, you need a lot of symmetry in ambient space, and Song didn't assume anything about ambient space except for some dimension bounds. And there is another line of arguments that's used, and that's developed by Chodosh, Getover, and Maximo, where they try to understand the geometry of minimal surfaces of bounded index by studying the degeneration of sequences of such surfaces. And this fundaments the approach I want to take here. So for the statements of the main results, which I'm going to talk more about on part 2, the first result states that in any closed tree manifolds, when we have the area and index bounds for a embedded CMC surface control the genus. So, and it's interesting to note that this bound C really depends only on the area bounds and on the manifold. So it doesn't depend on the value of the mean curvature. And the second result is in the particular case where M is spherical, that is when it has phi in the fundamental group and sigma is non-minimal. So it has a mean curvature at least, let's say, some eta greater than 0. We can drop the area bound and we actually get an area bound for these surfaces. So, which depends only on this lower bound for the mean curvature, on the index bound, and on the ambient manifold. Now, this second result is something that doesn't hold for minimal surfaces. So, thank you for your attention. I hope to see you in the next video. Now, to finish, I'm gonna pass through the references and you can stop to look any of them up.